Welcome back. This is video lesson number 13. Today we're going to be talking about power series. Let's get started. So a power series is a function where every input gives me a different infinite series. So it's a function that looks like this. The terms are, I have a coefficient an, and then I have x minus some number c to the n. So each term is a different power of n, or of x rather. This number c here is called the center. We'll talk a bit about that later. But you should think of it as it's a infinite polynomial sort of. I have powers of x here, and the powers tend towards infinity, right, as n goes to infinity. So I have an infinite sum of powers of x. And then each of these numbers are just the coefficients, and they can be any real numbers. So like I said before, every time I plug in a different value of x, I get an infinite series. So here's an example. I have a power series, f of x equals the sum from 0 to infinity of n times x minus 2 to the n. So the center here is 2, or this is c. And this n is an, from if you're thinking about it in terms of the formula on the previous page. So, okay, here's the question. Does this power series converge at x equals 9 over 4? So the way I find that out is, well, I just plug in 9 over 4 in for x in this series. So I get the sum. N stays the same. X minus 2, if x is 9 over 4, is 1 over 4 to the n. So this is just a normal old series, and we could use techniques from that we already know to figure out whether this series converges. Right, n over 4 to the n. It turns out this does converge. If you want, there are lots of ways to prove this. You could use, for instance, the ratio test. And actually, I'll note this again in a little bit, but the ratio test is what we use pretty much all the time when we're talking about power series. Okay, and so when I plug in another value, so let's say I plug in x equals 3, I get f of 3, which is the sum of, well, when x is 3, I have 3 minus 2 to the n, so that's 1 to the n, so I just have the sum of n, right, because this entire thing becomes 1. And this series diverges. It's the sum of all of the numbers. So of course it diverges. If you really want to reason it, you can say it diverges by the divergence test. Okay, so that's the game. I have series, and I can plug in some values of x, and the series will converge, and then possibly for other values of x, the series diverges. All right, so a lot of the time we'll be interested in, for a given series, for which x does it converge and for which x does it diverge. So working towards that, we have the notion of a radius of convergence. So like I just said, a power series may converge and diverge for different values of x. Something to note is that it always converges when x is equal to c, because when I plug in x equals c, I get 0 here, so that my series is just the sum of zeros, which obviously converges. Now, the radius of convergence is going to be a number. I'll usually use capital R to denote it, and it satisfies the following. For values of x that are closer to c than r, that's what this means. So whenever the difference of x minus c is less than r, I get absolute convergence. And whenever I have a value of x that is further away from c than r, then the series diverges. So here's the picture you should think of. So this is my number line, and I have c, right? C is the center. And then I go a distance r backwards to c minus r, and then a distance r forwards to c plus r. And so the radius of convergence is the number such that for every value between, so maybe this is the open interval, between here and here, everything in here, whenever I plug any number in here into the series, I get something that converges absolutely. and whenever I plug a number outside the interval on either side, I get a series that diverges. Okay, turns out there is always a number number r that satisfies this. Okay, but it is possible that r is equal to 0, meaning that the series only converges when x is equal to c. It's also possible that r is infinity in the sense that the series converges for all x. So r is either 0, meaning the series only converges at c, or it's a positive finite number, meaning there are some x for which the series converges and some for which it doesn't. And then, or we could have r equals infinity, meaning the series converges for all x. So a related notion to the radius of convergence is the interval of convergence, which is a more precise way to gather the information of where the series converges. So here's my number line again. I said that there's the center, and then there's c minus r here, and c plus r. The radius of convergence doesn't tell you anything about what happens right at these endpoints. Right, remember in the previous, I use strictly less than, strictly greater than. So I'm not talking about what exactly happens at these two endpoints. So if I can find out whether or not the series converges here and here, I can put all this information into an interval, meaning it's just all the set of points where the series converges. So that's called the interval of convergence. And it's, like I said, it's always this open interval plus possibly one of these two endpoints. So the way you find the interval of convergence is first actually you compute the radius of convergence, and then you need to check these endpoints to find the interval. Okay, so we're going to do two examples of this right now, but the idea is you always use the ratio test, almost always. Here's the first example. I want to compute the radius and interval of convergence of this series, the sum of x to the n over 2 to the n. Like I said before, I'm going to use the ratio test, and the idea is don't specify what x is, leave x as a variable, and then we're going to sort of solve for x later. So, ratio test. Remember the ratio test, I take the n plus first term of the series, which is going to be x to the n plus 1 over 2 to the n plus 1, and I divide by the nth term, x to the n over 2 to the n. Put all that in absolute values. And then we take a limit as n goes to infinity. So this is equal to the limit as n goes to infinity of, I have x to the n plus 1 divided by x to the n, that's just x. And then 2 to the n plus 1 divided by 2 to the n is just 2. Okay, so this doesn't have n's in it, so the limit is going to be, right, I'm taking the limit as n goes to infinity. So the limit is literally x over 2 absolute value. And now this converges. Remember the ratio test says this converges absolutely if this limit is less than 1. So this is kind of the thing that we solve for x. All right, if the absolute value of x over 2 is less than 1, then I can multiply both sides by 2, and I get that the absolute value of x is less than 2. Now, what this is telling you is this series will converge if x is less than 2 in absolute value, and also if I put a greater than symbol here, the ratio test would tell me that this series diverges if x is greater than 2 in absolute value. So we get that the radius of convergence of this series is 2. It's the number here. Okay. Now, to find the interval of convergence, I need to check the endpoints of the interval. The center here, I should have written this down earlier, the center is 0. And so I need to check 0 plus 2 and 0 minus 2. In other words, I need to plug in x equals 2 and x equals minus 2, look at the series that I get, and then determine whether they converge or diverge. So we'll start over here. Check the endpoints. So at x equals 2, Actually, let's just say plug in 2. What do I get? I get 2 to the n on top, so this is going to be the sum from 0 to infinity of 1. And this diverges but by the divergence test. And then if I plug in negative 2, on the top I'll have negative 2 to the n divided by 2 to the n. That's the sum of negative 1 to the n. And this also diverges by the divergence test. And so what I found is the series doesn't converge at either endpoint of this open interval from negative 2 to 2, and so the interval of convergence is just the open interval from negative 2 to 2. In other words, it doesn't contain any of the endpoints. So here's our answer. Okay, this is the pattern that you'll almost always do when you're trying to find the interval of convergence of a power series. You do the ratio test, and then whatever limit you get for the ratio test, you set that to be less than 1, because that's when the ratio test tells you that the series will converge. You use that to solve for x in the sense, so you'll get absolute value of x is less than something, and that'll tell you the radius of convergence. And then you need to check the endpoints of the interval to see, and to do that you just use regular old series tests like the divergence test or limit comparison, any of those things, to check whether the series converges or diverges at the endpoints. And that gives you the interval of convergence. Here's another example with a slightly different series, the sum of x to the n over n factorial. Let's do the same thing. So I do the ratio test, meaning I'm going to take the limit as n goes to infinity of the absolute value of the n plus first term, so x to the n plus 1 over n plus 1 factorial, divided by x to the n over n factorial. All right, let's simplify this. I get the limit, and all right, so x to the n plus 1 divided by x to the n is x. N plus 1 factorial divided by n factorial, remember that's just n plus 1, because n plus 1 factorial is n plus 1 times n factorial. Okay, so I take this limit and I get 0. Now, okay, I just told you that we have to solve this for x, right? We have to set this less than 1 and then solve for x, and then we get some interval. But what this is telling us is no matter what x is, the ratio test always tells me that I get a number less than 1. I get 0, meaning that the series converges for all x. Right? Didn't matter what x was here, I always get 0, so I always get something less than 1. So if you want to say the interval of convergence is something, you can say it's the entire real line. I don't know. Or you can just write the series converges for all x. That's fine. Or that the radius of convergence is infinity. All of those are the same thing. Okay, let's move on to an important example, which will lead us to the notion of a power series expansion for a function. So let's start with this power series, which is just the sum of powers of x. So this, if x is a fixed number, in other words, I'm not thinking of this as a function of x. If x is a fixed number, then this is a geometric series, right? I could have written it as r to the n and thought of it as a function of r. But anyways, it's geometric and the common ratio is x. Now, remember that when the ratio x here is less than 1 in absolute value, that this series will converge, and actually it'll converge to something we know. It'll converge to 1 over 1 minus the common ratio. So we have that for any x less than 1, this power series, rather, which now I am thinking of a function of x, thinking of as a function of x, is equal to this function. So this is our first example of what's called a power series expansion. So I have a function, 1 over 1 minus x, and I've expressed it as a power series, and the center of the power series is 0, right? I have x minus 0 to the n here in this power series. So once we have a power series for one function, so we know this, we can take this power series and use it to find power series for other functions. For example, if I replace x here by 2x, I get this, right? So in this expression, I've replaced x by 2x. I get 1 over 1 minus 2x is equal to this series. So I found a power series expansion for 1 over 1 minus 2x. And it's important to note that this is valid for a different set of x, right? If this expression on the top holds for x less than 1, then this one will hold when 2x is less than 1 in absolute value, which is the same as this, x less than 1/2 in absolute value. So the last thing to note about power series is that I can take derivatives and integrals of them easily. So if I have a function given by a power series, so instead of thinking of this as a power series, maybe I can think of it as the power series expansion of some function. If the radius of convergence is a positive number, meaning the function converges not just at the center but elsewhere, then the function is differentiable on this interval, which also means that it's integrable. And the way I find the derivative and integral is term by term. So the derivative I find by taking the derivative of this term and then just making it into a sum. So the derivative of an times x minus t to the n, using the power rule, is just n times an times x minus t to the n minus 1. Just taking the derivative of this. Notice that the series starts at 1 now because the first term here, this should have started at 0, the sum from 0 to infinity. The first term is a constant, so when I differentiate it, it goes away. So here's the derivative, and the indefinite integral is given also term by term. So I just find the antiderivative of this using the power rule for antiderivatives. I get this. And then there's a constant that ends up front, and this is the constant of integration. Okay, so to summarize, if I have a power series, I can differentiate the power series or integrate them term by term, and then I get new power series that have the same the same radius of convergence, not necessarily the same interval, but at least the same radius. Okay, this concludes the crash course in power series. What follows are 2 examples of using these 2 ideas to compute power series expansions for 2 functions. I know that this was very quick, but the main thing that you need to be able to do is first find the interval of convergence and or radius of convergence of a power series, and next do examples like the ones we're about to do where we find power series expansions for functions. So here's the example. I want to find a power series expansion for 1 over 1 minus x squared at x equals 0. So what I'm going to do is I'm going to start from the power series from 2 slides ago. I know that 1 over 1 minus x is equal to the sum from n equals 0 of x to the n. And then I notice that if I differentiate this, so the derivative of 1 over 1 minus x, it turns out it's exactly 1 over 1 minus x squared. Using the chain rule, right, I have 1 over something, I differentiate that, I get 1 over that thing squared with a minus sign, but then the derivative of 1 minus x is minus 1, so the minus signs cancel, and I get this. So if I know that the derivative of 1 minus x is the power series, the function that I want to find the power series expansion of, by what we said in the previous slide, I can just differentiate this term by term. So I get that 1 over 1 minus x squared is the derivative of the power series that gives me 1 over 1 minus x, so which is a sum of x to the n. And remember, what I do is I just differentiate this term by term. I get a sum starting at 1 because the first term here is a constant, which when I take the derivative will get me 0. I have n times x to the n minus 1. And that's it, right? So now we're guaranteed that this is a power series for this function because I took the derivative of one that I already had a power series from. And remember, the radius of convergence stays the same. So this was true for x less than 1 in absolute value, so this is also true for x less than 1 in absolute value. So that's how this goes. We start from a function that we already know the power series of, which in this case was this one, and then we differentiate or take an indefinite integral to get to the function and a power series for what we're trying to find. This is the last example. Let's find a power series expansion for this function, the natural log of 1 plus x, centered at x equals 0. Okay, I'll note that I've had everything centered at x equals 0 so far because that's usually the easiest to work with. It won't always be the case. I think when we're doing exercises in class, we will see examples, several examples when c is not 0. Anyways, so somehow I need to start from this and take derivatives and maybe make a substitution and get to 1 over 1 minus x, because that's the thing that I know how to find a power series for. All right, remember it's equal to this. So notice that if I take the derivative of the natural log of 1 plus x, I get 1 over 1 plus x. And that's almost 1 over 1 minus x. What I'm going to do to get it to look like 1 over 1 minus x is put two minus signs. So write it as 1 minus 1, a minus x, like this. The reason I'm doing this is because now I know that a power series for this function is given by the sum from 0 to infinity of this, but with a minus x in place of x. All right, and this is for x less than 1 in absolute value still, because if minus x is less than 1 in absolute value, then so is x. Okay, so that's how I found a power series for the derivative of the function that I want to find a power series for. So to get to the natural log of x, I'm going to take an integral. If I want, I can think of it as a definite integral, but let's just do it as an indefinite integral. It's the integral of 1 over 1 plus x, which by my power series rules is just going to be the term-by-term integral. So we'll write it as a sum of integrals of each term. Remember, and then I have plus a constant because I'm taking an indefinite integral. So minus x to the n is minus 1 to the n times x to the n. Minus 1 to the n is constant, and so I get the sum from 0 to infinity of, when I take an indefinite integral, I'm going to get minus 1 to the n times x to the n plus 1 all over n plus 1, and then plus c. Finally, to find c, we can plug in a number for x and figure out what we should get. So if I take x equal to 0, I get here, right, if x is 0, then this entire thing is 0, and the natural log of 1 plus x is also equal to 0 because it's the natural log of 1. And so this tells me that, right, if I plug in 0 on this side and in here, and I got 0 here and 0 here, this tells me that c has to be 0. Okay, so in other words, the power series expansion for the natural log of 1 plus x is just this. Okay, and c is 0. So, okay, that was probably a bit quick. I encourage you to either go back and watch the video again, or go back and pause at parts that you need to review. Unfortunately, I didn't have a lot of time to give exercises for you to do. I just really wanted to illustrate the technique for finding these power series expansions. We'll have, like I said, we'll have lots of opportunities to do problems like this in class over the next couple of days. And as always, if you have any questions about it, you can ask me then or during office hours, and I'd be happy to answer them. So this was the last video lesson of this summer semester. I hope you enjoyed this series, and if you have any feedback about it, you're more than welcome to email me Let me know what you thought of the videos, if you thought they could be better in any way. I'd be happy to hear things like that. So thank you very much, and I would usually say see you next time, but I'll just say bye.